All right, we are going to start chapter number 5 here, and we are looking at question number 1. And question number 1 asks, why wouldn't you use SPTP to describe thermal bioeffects? So let's just do a quick review of SP and TP. So remember, when we're looking at our spatial considerations, we know that the very, very center of the beam is the most intense area for ultrasound energy. And if we could kind of look at this from the side, we would see something like this, where these are the edges of the beam, and then this represents this very center part. So spatial peak is where we see the most intense sound energy. When we look at a pulse, we're going to see that the pulse has different intensities along time. So this is time going this direction. So we can say this is like 1 second. And as time goes on, there are going to be different intensities along that time. And then remember, because we're doing pulse wave, we have this gap in sound energy being used as well. So that also factors into some of our intensity considerations. So we've got this variation in intensities, and we know that because amplitude is related to intensity. And we can see that this amplitude is less than this amplitude. So we will see that the temporal peak is at the very highest amount of intensity and amplitude over time. So that's our temporal peak. Now, what we do use for bioeffects and for measuring thermal bioeffects is spatial peak temporal average, SPTA. And SPTA is going to take the time that the pulse is on and that the pulse is off, and it's going to average the intensity over that on and off time. So why don't we use SPTP? This moment in space and this moment in time is just a fraction of the sound energy that the patient is experiencing. So we know that we're always giving them that spatial peak. There's no way to only kind of give them the edge of the sound beam, but we also know that they're always getting a mix of intensities over time. And so what we really are concerned about is what is their average of getting sound energy, not getting sound energy, and what does that look like over the area of the beam. So if we were to use SPTP, we would only be capturing this very second in time, none of this other energy that they're getting, and we're not accounting for the time that they aren't ever getting energy, which is why SPTA actually represents the sound energy that the patient is actually getting. All right, question number 2 asks us, how is Imax determined? So Imax is a function of the temporal considerations. So we'll draw our beam in here again. I'm going to stop there. And again, we have to remember that over time, the intensity of the pulsed beam is going to be different. It's going to vary. So these intensities are kind of on the lower end, where these intensities are on the higher end. So when we are looking at temporal peak, we are looking at that very moment in time where the highest intensity is recorded. So this is our temporal peak. What Imax does is tries to understand where the highest chunk of intensities are. And so it would look at this whole area over here. This part of the wave, this amplitude of the wave, this is going to carry more intensity in general compared to this part. And so Imax is going to look at more of a section of the wave over time versus looking at the absolute peak. But the Imax will include that peak part because we are looking for the largest intensities of a section of the wave. All right, and we are on question number 3. Number 3 says, why does, when pulsed and continuous wave sound beams have the same SPTP intensities, the continuous beam has the higher SPTA intensity? So let's take a look at a pulsed beam first. And let's put a little space in there because it's pulsed. We'll put our other one there. All right, so when we are looking at a pulse beam, we're just going to take a look at the temporal considerations. Remember that this is time going across here, right? And we have a variation of intensities over the time of the pulse. So first thing that we know, we've got our temporal peak. So we'll label that TP. And I'm just going to give this an arbitrary value so we can kind of see how it works out without having to speak in like completely abstract. So we're just going to give this kind of a random value of 10. And by giving a value of 10, yes, it should have a unit, but again, we're just not going to complicate it. We're just talking in generalized numbers. So we'll give the temporal peak a 10. And then pulse average is going to take the values of the intensities found over the whole pulse and average them together. So this is our pulse average. And then we have temporal average, which is going to take the average intensity found in the pulse and during the listening time. So this is our temporal average. And so like I said, we kind of gave the peak a arbitrary number. Let's go ahead and we'll just call this intensity 2, and we'll say 4, 6, and 8. Again, just because we're getting probably bigger intensities as this pulse moves on, at least in this example. And then we know the intensities during this period here are going to be zeros, right? Because there's no intensity, there's no sound beam there. So that's going to have an intensity of 0. And I'm just kind of putting those zeros at the same intervals as what our pulse wave is at as well, measuring those measuring those different intensities. So if I said that, we can calculate the pulse average, again, using our generalized numbers. We know to average something, we take the value, so 2 plus 4 plus 6 plus 8, and we'll include that 10 because that's our peak. So 2 plus 4 plus 6 plus 8 plus 10 equals 30, right? And then to get the average, we have to divide by the number of values that we had added together. So we added 5 numbers together, 30 divided by 5 equals 6, and that would be our pulse average. If we wanted to do our temporal average, again, we would do kind of the same thing. We would take our 2 plus 4 plus 6 plus 8 plus 10, but now we have to add in our zeros. So we did 4 more measurements of 0. So that all still equals 30, but now we are going to divide it by 9. And roughly 30 divided by 9 is going to be like, we'll just call it 3.1 for the fun of it. 3.1 then is going to equal our temporal average. So right now we can already see by including these zeros here, temporal average is less than our pulse average. And then all of that is less than our temporal peak. That all makes sense. But the question or the commandment that we were talking about basically was that if a pulse and a continuous wave have the same SPTP, then the continuous beam should have a higher SPTA. So let's look at what that would mean. So here is another space for a wave, and this time we're just going to draw our continuous wave. And we're going to say that this continuous wave has a bunch of peaks, right, at 10. And the idea again is that we're going to have this temporal average going through here. So about roughly about the same size. So spatial peak, temporal peak is the same, 10 and 10. That makes sense. We're fulfilling what the question was asking. But now let's take a look at that temporal average. Now we're going to add 10 plus 10 plus 10 plus 10 plus 10 plus 10. And that's going to equal 1, 2, 3, 4, 5, 6, 60. And then we added 6 together. So 60 divided by 6 equals 10 for our temporal average on this one. And that is definitely more than this one. And so what really the short of the answer is that the continuous wave never has this off time here. And because it never has that off time, it just ends up being a higher value because we're not averaging in a bunch of zeros where there's actually sound beams still occurring in the continuous wave. So continuous wave with the same SPTP as a pulse wave will have a higher temporal average than the pulse wave. All right, question number 4. And question 4 says, what is the rank of intensities from largest to smallest? So whenever we think of largest, we have to think the peaks. So spatial peak plus temporal peak is going to be our absolute largest. We also know then that averages are going to be the smallest. And remember, the temporal average is the one that includes the zeros, the off time, so that is going to be our smallest. I would say these two are probably a couple of the more important ones to know in just the general sense of why SPTP is the biggest with the peaks and the SATA is the smallest with the averages. And then, of course, we do need to know our SPTA, which is important for our bioeffects. So those are probably the 3 combos that you absolutely need to know and where they kind of land in the spectrum of greatest to smallest. But then as far as the other ones go, we have our spatial average temporal peak, and then we have our spatial peak pulse average and our spatial average pulse average. And so we'll see that the temporal pieces of it kind of have a bigger impact on it. We talked about that in question number 3 with the averages and temporal average, pulse average, and then just looking at the peak. So I think the biggest thing to remember is TP, TP, PA, PA, TA, TA. And then it's just SP, SA, SP, SA, SP, SA going down the other side because peaks are always going to be bigger than averages. So that might be helpful for a way to memorize this list. But again, SATA, SPTA, and SPTP are going to be probably the 3 that you're really going to need to know for your boards. The second part of 4, so 4A, is asking why does the book only have 5? And it really just depends on the resource. That's what the author of the Green Book decided to use. This is the, I'll show you the cover here. This is the Stephen Penny Tracy Fox book. They, I think, are coming out with another edition shortly here. But again, I'll just show you this page here. They do list all 6 of the intensities, but you'll notice that they skip IMAX. They don't actually even talk about IMAX in there. So it really just depends on the resource that you're using. But that is where that information comes from and how the other intensities fit into the rankings. And then again, just know that SPTP is the biggest, SATA is the smallest, and SPTA is the one we use for bioeffects. Right, moving on then to question number 5. And this one asks, how are intensities combined? Well, intensities are combined based on taking a measurement from the spatial consideration and then also taking a measurement from the temporal consideration. So let's draw our pulse wave here. And then I'm going to draw, we'll draw the kind of that circle that we've become familiar with the very center being our spatial peak. And then I'm going to draw the side profile of that as well. All right, so something like that. And let's do some color coding here. We will do green in the center of the circle. Green at the center of the top here is going to be spatial peak. And then we'll do purple kind of on the edges here, which kind of represent these areas here. These are going to be our spatial average. And we'll use blue, very peak here, to look at our temporal peak. And we'll use orange to represent our pulse average. Again, just averaging out the intensities during the pulse only. And then we'll get one more color. We'll use brown to look at our temporal average, which is going to include the off time. So when we are combining the intensities, we are going to take one spatial consideration and one temporal consideration. So we will see that we can get an SP combined with all three of the temporals, and we'll see that we will have an SA then combined with all three of the temporals. And then we can just add a temporal to each one. So those are our main considerations for combinations of intensities. I'm going to leave this up for question number 6. Question number 6 does ask, so question number 6 says, what is the difference between spatial and temporal measurements? Well, again, spatial is considering the beam in space, and temporal is considering the beam over time. So again, if we had a little camera here and we were watching the beam go by in time, this little camera maybe is measuring intensities as that goes by. We would see a variation in the intensities as the beam goes by in consideration to that time of it passing. So very different things that are occurring here. The spatial part of the beam, so like if we have our transducer and the beam is coming down like this, this area right here would represent this area here where these edges are also these edges. So the very center of the beam is where that spatial peak is. The patient is always receiving the spatial peak and the spatial average, but they're not always receiving the temporal peak. They're not out, and then we're averaging out the rest of the things that they are receiving. So all just kind of has to do with, I guess, considerations to space and time. All right, we are going to continue on with question number 7 here, and I'm going to leave some of this stuff up because I think it'll help to answer it. So question 7 says, how should I think of pulse average in relationship to spatial peak average? There's a little bit of a disconnect with this question asking about the spatial peak average, and so I'm not 100% sure what the question was trying to get at, but I will try to do my best with what I think you're trying to get at. So again, we're back to the spatial peak and spatial average. Spatial peak, spatial average are different things. The peak is going to be the most intense center part of the beam, where spatial average is going to be the average from center to edge. So it's going to include that super intensity in the center, but it's going to also include those very low intensities on the edge. And we're going to get an average in there, which should be lower than the peak. 7a does say I need a better way to visualize this. So I am going to show you just one thing. I think this is talked about in your green book as well, and hopefully it shows up on here. So I've got a flashlight, and you guys can probably kind of see that there's a really, really, really bright section here from the light, and then it kind of gets a little fuzzier out here. So the very center of this right here, that would be our spatial peak. And if we could think of, if this is our flashlight, and we've got this really intense area coming down here, that would be this area here. And then we kind of have this, fuzzier part on the outside of it that you can kind of see traced there. Those are going to be kind of the weaker intensities, right? But then the average is looking at that all the way across. So if we gave this center a 10 and this outside here a 2, 10 plus 2 is 12 divided by 2. Just to use, again, generic numbers, we could say that the spatial average is 6 and the peak is 10, because the average is going to consider all of this intensities from center to edge. So I'll just bring this up here so you guys can see it again without a bunch of coloring on it. So again, spatial peak is going to be right in the middle. Average is going to take those weak intensities on the edge, average them all together with all the way across the radius, I guess, of the circle. And so we need to think about the beam as coming out as a 3D expression of energy, I guess, and then recognize that there is a centerpiece and then weaker edges. So that is spatial peak and average, but then question 7 does want to know more about pulse average and how to think about them in relationship to another. And they really aren't related to one another, because that pulse average is only going to be about the actual pulse itself. And that's what we were seeing here. It's this orange line. When the pulse is on, let's get rid of some of this here. When the pulse is on, we're going to see that it has a variation in intensities. This is getting, more intense. It has a variation. And we know when the echoes come back into the ultrasound machine, these kind of like negatively displayed pieces are demodulated. And what we kind of end up seeing is something like this. One more to match that. All right, so now we've got something like this. And if we were to give all of these their own value, let's say 2, 6, 4, 8, and 10, the pulse average would take an average of all of those. And again, to get an average, we add that together. So 2 plus 4 plus 6 plus 8 plus 10, that's going to equal 30. Divide that by 5. And then our pulse average would equal 6, because we are averaging the intensities across the duration of the pulse only. So that might help you understand how we're getting those averages. We're kind of looking at the intensities. Remember, intensity is directly related to the amplitude. We can see the amplitudes are increasing here. So probably the biggest part is remembering that there is variation within the pulse as far as intensities go. And then your pulse average is just averaging the intensities found only in that on time during the pulse. So very different concept from the spatial, which considers the beam and how it behaves in space. Pulse average considers the intensities found within time of just the pulse. All right, now we are on to question number 8. And question number 8 says, question 8 says, will we ever use a hydrophone as a sonographer? Short answer, no. Again, we've got our transducer, beam is coming out. We've got kind of the center intense area. And this hydrophone, just pretend my pen is the hydrophone here, it's going to be this tiny little transducer on the end of a little needle. And you can stick it in to different parts of the beam, right? So if I stick it in right in the edge here, the hydrophone would recognize what the intensity is on the edge. And then if I move it towards the center of the beam, it would be able to measure those center peaks, those spatial peaks. And then, I can move it around and I can get very exact intensity measurements while I move this around in space. Now, the other thing that we know is that we're going to have different intensities coming down, right? So if I hold it here in the spatial peak, at some point, I will get that temporal peak during that time as well. And so we would be able to measure that. We would be able to record all of the pulse as it goes by my pen. So then I could record the pulse average. And then we would also record those listening times as they go by my pen. And we would be able to calculate the temporal average from that as well. So no, as a sonographer, you will never use a hydrophone. This is probably going to be more biomed, people making the transducers, maybe physicists, if you have somebody coming and testing your transducers, but not as a sonographer. But the hydrophone is the tool that measures the intensities of the beam and verifies that we are not putting our patients at risk by using the ultrasound energy created by the machine. All right, question number 9. 9 says, how should I think about temporal peak and IMAX? I did talk a little bit about this earlier when I was talking about how IMAX is determined, but we'll just cover it again here. So again, remember our pulses have different intensities along the time of the pulse. And so temporal peak is going to be the absolute max. This is as big as the pulse gets. That's going to be the temporal peak. What the intensity max is looking at is where in this pulse are we getting the most intensity. So that would definitely include the temporal peak time, and maybe it's kind of like this area here. That's going to be our max area because that's where we're seeing the most amount of intensity. So the intensity max or Imax is not really anything that you probably even really need to know, but that is how it's figured out. That's its consideration, is that it's looking at the strongest chunk of the pulse, where temporal peak is just the absolute intense part of it, and pulse average is looking at all of the pulse. All right, next up we've got question number 10. And number 10 says, why are there so many ways to measure intensity? You know what, there are a ton of ways to measure intensity, but I think we've covered them a lot in the last question, so I hope that you've been kind of following along with all the questions leading up to this. But all of them are there because all of them affect the patient differently, and all of them need to be considered. So again, remember, we've got our beam coming out, we've got a very intense spatial center, the spatial peak of the beam, and then our pulse is going by and stopping and then going by again. So we do need to consider that the patient is receiving all of this, right? With the most intense part of it, the spatial peak. So there's at no point does the patient not receive all of the beam. So that's usually, again, why we are most concerned with spatial peak. And then as far as the pulse goes, the important part of it is that the patient is getting pulses and some off time too. And so we, at least for bioeffects, are concerned with what the patient is receiving on the whole. And so they are getting the pulse and the off time. So that is why we look at spatial peak, temporal average for bioeffects. But we do need to understand too that there are times that they are getting very intense temporal intensities. There's considerations to take in when we're just looking at the pulse average, like just the on time of the pulse. And so it all just kind of plays into bioeffects in general, but our big one is SPTA. And I don't know that I have a much better answer for you than that there's just multiple ways to consider it. And so they measure them all just to make sure that we are staying within a safe range of ultrasound energy for our patients. All right, next up we are on question number 11. And question number 11 is probably a little bit more of a statement, but I did still want to talk about it because I think this is going to be helpful for everybody. So question number 11 just says memorizing the 10 commandments. And when you read the book, it's like, these are the only things you need to know about intensity, just focus on these things. And our green book was written by Dr. Edelman, and Dr. Edelman is probably best known for that green book, and then also for the physics SPI seminars that he used to put on. Dr. Edelman sold his company a while ago and has since retired. So now the company is ESP Ultrasound, and I think I told you guys earlier in the semester that I do work for them, so full disclosure here. So they have Richie Palma now is doing the physics, but it's basically the same material because a whole lot, things have changed, but not so drastically. Physics is still kind of physics. Anyway, for the seminar, ESP gives all seminar attendees a workbook that goes along with the registry review. And Dr. Edelman adjusted his 10 commandments down to just 3. And so I will show those to you here in a second here. So there are 3 commandments of intensity that you really, really should know. So yes, there's 10 in your book. Arguably, most of them aren't even going to be tested on. So he's narrowed it down to just 3 that he thinks everybody should know. And I would say I, for the most part, agree with it. So the first one is that intensities may be reported in various ways with respect to time and space. So intensity is reported in spatial considerations and temporal considerations. So we'll just put time. All right, so that's the first commandment of intensity. We have space and time. The second commandment is that intensity is the key parameter with regard to bioeffects. The different intensities are important in the study of bioeffects. SPTA intensity is the most relevant intensity with respect to tissue heating. So SPTA measures tissue heating. And this is important for bioeffects. So that is commandment number 2. And then number 3 says peak is greater than average. So we will see that SPTP is the greatest, and SATA is the lowest intensity. And those are the three commandments that Dr. Edelman has adapted into the workbook. So I would agree with all of this. I am going to add probably two more things onto it. First one, intensity for a unit is going to be watts per centimeter squared or milliwatts per centimeter squared. I would say that is a fourth thing you should know. And then the fifth thing that I do think you should know about intensities is that we have some guidelines that we need to fall under and that we know there are no bioeffects from. So no bioeffects occur when we have an unfocused beam and the SPTA is less than 100 milliwatts per centimeter squared. So there's no bioeffects when the SPTA is less than 100 milliwatts per centimeter squared. We also know that there are no bioeffects in a focused beam when the SPTA is less than 1 watt per centimeter squared. And what we find with both of these, if we keep the SPTA under these limits, we will see that we keep the temperature rise to be less than 1.5 degrees Celsius. And remember that this temperature, this thermal mechanism is always being monitored by the TI on the machine. So up in the corner, you'll usually see like TI followed by a couple numbers. And remember we have the TIC, the TIB, and then the TIS. We'll see that the TIC and the TIB are including bone in their calculations. And so bone does absorb a lot more sound energy. So we have to be really careful when we're around bone. But again, we are still monitoring our TI value and making sure that we're not going over that 1.5 degrees Celsius. So these three are the three I would focus on. You should probably already know this just because we've been studying parameters and it falls into the category with that. And then I would spend some time with this. This is going to be part of like the QA, patient safety, ALARA. You might have some questions on this information here. So I would make sure that we know the SPTA less than 100 milliwatts per centimeter squared for unfocused, SPTA for focused less than 1 watt per centimeter squared, keeping the temperature rise less than 1.5 degrees Celsius. Okay, and then we've got our last question, number 12. And number 12 says, can you go over the temporal average intensity and pulse average intensity? Especially while looking at the graphs, I'm kind of having trouble with the combining spatial and temporal factors section as well. All right, so for your second part of your question, having trouble combining spatial and temporal factors, go look back at number 5. I did cover that pretty in depth in there of combining those, and I think it kind of went into question 6 a little bit as well. So if you didn't watch all the questions, go back and look at 5 and 6. And then can you go over temporal average intensity and pulse average intensity? We can absolutely talk about that one more time here. Let's draw. I always want to put more pulses in. And then we'll just start one over here. Okay, so get some colors out. Again, pulse average is only looking at the time that there is a pulse present. So pulse average is going to only be pulse. Temporal average then is going to be both on and off time. So we're going to include the time during the pulse, and we're going to include that off time. I had kind of shown this in another idea that when we demodulate, we flip these kind of negative intensities up, right? So if we were to flip these up, it might look something like this. If I was going to redraw this pulse as demodulated. So now we are still looking at pulse average. And then we are looking at our temporal average. And The big difference between these two is the fact that one has all the on time and one has the on time and the off time. So again, if we were to just give random intensity values to each of these peaks, we could figure out the pulse average as being 2 plus 4 plus 6 plus 8 plus 10. That equals 30. We have 5 values, so divide by 5, and we would find that our pulse average equals 6. And again, these are just kind of mathy ways to look at this. So we are averaging the intensities that we find through there. Where temporal average, we got to consider the fact that there's a 0, a 0, a 0, a 0, a 0. So then when we do the temporal average, we have to not only take these values, but now we also have to average in our zeros. So 30 still, plus 0, plus 0, plus 0, plus 0, plus 0, still equals 30. But now we're averaging that over 10 values, or 10 check-in points, we'll call them. So 30 divided by 10 equals 3, and that's our temporal average. And so we can see that the temporal average does include that off time. Temporal average is lower because of that, so that temporal average intensity is lower than our pulse average intensity. The patient is always receiving the pulse and that off time, which is why we consider spatial peak plus temporal average for our bioeffects.